Dear ESANN participants, I'd like to present the paper Object-Centered Fourier Motion Estimation and Segment Transformation Prediction by Professor Yarrow, Behnke, and myself. Why do we need to be able to predict object movements in video? An important part of our motivation is to enable autonomous robots to have a better understanding of the near future. This could, for example, be important for a soccer-playing robot who has to not only be able to anticipate the movement of the ball, but also the movement of its teammates and opposing playing robots. Similarly, an autonomous drone needs to be able to have some understanding of the movement around it to be able to plan its path. However, unfortunately, current machine learning systems often produce blurred predictions. Our question now is, can we predict object movement in videos without suffering from the blurriness that we often see in current machine learning approaches? To tackle this problem, we assume to be working with a pre-segmented object. We estimate its centroid as well as translational and rotational velocity based on phase correlation. That means we compute the Fourier transform of the current input image and the previous input image and move on to compute the correlation in the phase, which gives us information about the displacement as well as the rotation between the two images. The displacement and the rotation velocities and their changes are then modeled in a gated recurrent unit. We require such a unit because the correlation approach is limited to pixel level accuracy. However, objects may move at sub-pixel level accuracy, and therefore we have to integrate information over more than just 2 frames over time. Finally, we have to transform the current image to produce a prediction. Here we show that we can work with the 3-pass transformation method, which is shearing the phase to produce a rotation. This is an overview of our architecture. We show the input video, the context, in the bottom here. In this case, this is a moving MNIST digit, a 5. 2 digits then, or input frames, are used to estimate the centroid as well as the rotation speeds in x and y and the rotation theta. These estimations are then fed into our gated recurrent unit, which is using a residual term to correct the output from the video estimation. The corrected parameters are then fed into our transformation block, which is using the 3-pass method to produce our prediction frame. This new prediction frame is then again recurrently fed into the system to produce an entire video prediction over time. The shearing approach is shown here. By increasing the coefficient that's multiplied with the phase over different axes, we can produce a shearing effect. Multiple shearing effects lead to rotation, which is an extension of a previous work. Here we show a demo video. On the left, the ground truth, in the center, our network prediction, and on the right, a gated recurrent unit output, which is blurry, while the prediction from our system is not. Also note that we can handle rotation and translation at the same time. For more information, especially mathematical formula of the methods we used, please refer to the paper. It's available in the ESANN proceedings. You can also use the link that's shown here. Finally, this is an open source project. Source code is available on GitHub. Feel free to take a look. Thanks a lot for your attention.